So we finished off last week. We watched a couple of videos about Schrodinger's cat. We talked about the idea of quantum mechanics and this superposition where something can act like two things, a particle and a wave. And we saw how light does that a little bit. We talked about the Bohr model of the atom, which is nice because we can kind of visualize that. Funniest thing happened to me once. I was different school. I was explaining the Bohr model of the atom, and I mentioned that it was like the solar system. And this kid in the back, who I already knew he was a little unusual, he raises his hand, and I'm like, yes. And he says, how much does a telescope cost? I mean, you could imagine the path that his brain went on. Solar system, stars. I'd like to look at the stars. I wonder how much that costs. Wow. I was just flabbergasted. I didn't even know what to say. So anyway, we talked about... I said, well, it really depends on how big of a telescope you get, right? You can buy one probably for $5. That's not going to do much. Or you could spend a gazillion dollars on like the Hubble Space Telescope, right? Like, what on earth? Don't you have a phone? Can't you Google that just quietly by yourself? You have to ask me. Do I look like I'm the expert on pricing of scientific instruments or something? I have no idea. But the Bohr model is a lot like the solar system, and we like the Bohr model because we can kind of visualize that. Okay, and then we talked about light and energy, and we talked about properties of waves. So back in 1924, Louis de Broglie proposed that particles could have wave-like character in addition to their particle character. And this is most clearly seen with the electron when we do electron diffraction. We'll look at an illustration in a minute. Do you remember how the light, well, actually, we can go back to that. Let's go back to that slide. Remember how light interfered? Oh, it's way, way back. Maybe I shouldn't have done that, but now it's too late. Here we go. With light, you can get this diffraction pattern from the waves of light interfering with each other. We get destructive interference resulting in dark bands and constructive interference resulting in light bands. And what we'll see is that electrons do that as well. We're going to get an interference pattern. What's important to understand, and is a little mind-boggling, is that the interference pattern is not caused by pairs of electrons interfering with each other, but by single electrons interfering with themselves. Yeah, how does that work? That's an excellent question. So here's the idea. You have two slits and an electron source, and you pass electrons through the slits. And what you get is an interference pattern very much like that of the light. Okay? So, it would make sense, well, if electrons are like waves, then, it's multiple electron waves interfering with each other. But what they were able to do is they could take this electron source and reduce the intensity, reduce the number of electrons coming out, so that they could shoot out one electron at a time. So only one electron is going through here. And they would record still the interference pattern. You would still see an interference pattern even when you sent electrons through the slits one at a time. Like, okay, exactly. How does that work? Well, I can't explain that to you. I really can't. I have chosen not to think too hard about it. Now, obviously, if the electron is a particle, and we know that it is a particle, when it goes through here, it has to go through one slit or the other. But one of the ideas was, well, maybe it's somehow passing through both slits at the same time, and that's how it interferes with each other. So they set about to find out which slit that electron was going through. So they did something, well, this is the illustration of what we would expect if electrons behaved only like particles. So if you're throwing particles through here, the ones that go through the slit keep going. They're not running into anything. They're just going to keep going, and you should get two bright lines, one for each slit, and nothing in between. And that's not what we see. We see the interference pattern very much like that from light, which is electromagnetic radiation, which has very strong wave-like properties. So we're not seeing this. This wave nature of an electron is an inherent property of individual electrons. So the individual electron is a particle and a wave. It's a little bit like Schrodinger's cat that is dead and undead, and yet it isn't. Anyway, de Broglie predicted that the wavelength of a particle was inversely proportional to its velocity. So here we have the de Broglie relation, and this is something that you should memorize. So the wavelength of a particle is equal to Planck's constant, h, divided by the mass times the velocity. Yeah. Frequency and velocity, unfortunately, look very much alike. The velocity, nu, has a more curved line here than the small v for velocity. My apologies. Again, they should have consulted me on that, but they didn't. This is v, and I'm knowing it because it says proportional to its velocity up here.
What is Planck's constant?
Planck's constant, I believe we mentioned that before. Maybe we didn't. It's in the back of your book. Planck's constant is 6.63 times 10 to the minus 34 joule seconds. 6.63 times 10 to the minus 34 joules times seconds. Actually, I'll write that in here. 6.63. Your book gives a lot more decimal places than that, but that's good enough for most things. That's Planck's constant. Joules times seconds. It's not a very nice S, but you know, whatever. Joules times seconds. Yeah, they're physics units. Just deal with it. So the wavelength is inversely proportional to the velocity. It's also inversely proportional to the mass. So if you have an object with a large amount of mass, the wavelength is going to be very, very small. If you have a tiny, tiny particle like an electron, then the wavelength is going to be larger than, say, the wavelength of a baseball. So what is the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Assume that that length is 1.2 times 10 to the minus 10th meters. So we were just looking at the equation there. Lambda is h over mv. Did I leave something out? That's right, isn't it? H over mv. And h equals 6.63 times 10 to the minus 34th joule seconds. Now, I do not expect you to memorize Planck's constant. Okay, I'll give that to you if you need it. I do want you to learn the equation, though. So those are two things. Until you've learned the equation, you need to go look those up somewhere. They're not given in the equation. So they're telling us the de Broglie wavelength, and when they say that, that's your clue that maybe we should use the de Broglie relation. Okay, so this is lambda right here. This is lambda. and they're wanting the velocity. So we need to find v. So let's rearrange this equation. I'm still getting text messages from people who are doing silly algebra things. So let's just review what we should do with an equation like this. Here we're solving for v. V is on the bottom. Be careful. So we're going to cross multiply. We're like, there isn't a fraction on the left. Oh, sure there is. So by cross multiplying, we get lambda mv equals h. We want v by itself, so we divide by lambda m, and we get v is equal to h over lambda m. The common mistake is that people end up solving for 1 over the quantity, which is not the same. Do we have all the information we need for this equation? What's the mass of an electron? We would have to go look that up. Okay, I'm not going to make you memorize that. Mass of an electron, we'll just do 3 sig figs here. 9.11 times 10 to the minus 31 kilograms. 911. So the mass of the electron, 9.11. Oh, my short-term memory is just not very good. I'm going to double check that. I'm just looking this up on the back cover of the book. 9.11 times 10 to the minus 31 kilograms. Okay, so plugging these things in then, we have 6.63 times 10 to the minus 34 joule seconds. And down here, we have lambda being 1.2 times 10 to the minus 10th meters. That's the wavelength. And the mass being 6 point, no, that's the other number. 9.11 times 10 to the minus 31 kilograms. Okay, let's punch the numbers through. Again, you need to use the EE button on your calculator correctly. 6.63 EE34, change the sign. Divided by 1.2 EE10, change the sign. Divided by 9.11 EE31, change the sign. And so this comes out to 6.06 times 10 to the 6th. Now, did other people get the same number? Yes, okay, good. When you're doing a calculation like that by yourself, always do it twice. Okay? If you come up with the same number, either you're really good and consistent at making mistakes, or you got the right answer. If you get 2 different answers, go for best 2 out of 3. Occasionally you get 3 different answers, and then, yeah. Good luck with that. What are the units? Hopefully it's meters per second, right? Well, let's think about this. Here we have, let's just pull the units out. I have joules times seconds divided by, bless you, meters times kilograms. Bet you didn't know that bless you meters was a unit. Okay, so now we need a little trick. What are joules? Kilograms meters per second squared. So instead of joules, I'm going to write kilograms meters per second squared. Isn't that meters squared per second squared?
It is.
Yes, thank you. Because otherwise the units don't work out. So the kilograms cancel out. And this second cancels one of those, and the squared meter cancels that one in the bottom, and we're left with meters per second. So our units over here are meters per second. Now, if I were to give you a question like this on an exam, I would not expect you to know Planck's constant or the mass of an electron from memory. And I would put the units on those such that you could plug them into the equation and come out with the units that are given in the answers. I don't want a problem like this to be about messing around with units. We've done plenty of messing around with units. And this is getting too far into physics for me to expect you to be able to mess around with units, because many of you have not had physics. And it's not a prerequisite for this class. So I'm not going to make you learn physics more than I have to. Any questions? Is that fast? Yeah. 6 million meters per second. That's really fast. Uncertainty principle. So when you try to observe the wave nature of the electron, you can't observe its particle nature. When you try to observe the particle nature, you can't observe the wave nature. And this goes back to Schrodinger's cat. When you open the container, the cat is either dead or alive. Before you open the container, it could be either, you don't know. So the wave nature is shown by that interference pattern. The particle nature is indicated by its position, the position of the electron, which would be which slit is it passing through. If we can determine which slit that single electron is passing through, we've determined its position. When we do that, we no longer observe the wave behavior of the electrons. The wave and particle natures of the electron are complementary. The more you know about one, the less you know about the other. Some of you may say, could we just not know anything about either of them? Afraid not. So here's how they determined which slit the electron was going through. They shined a laser beam across the exit of these slits. When an electron goes through a slit, there will be a tiny flash of light as it passes through the laser beam. So you can see if it goes through this slit or through this slit. When the laser beam is on, all we see are the two bright lines which we expect from particles. If you do nothing but turn off the laser, this changes into an interference pattern. By observing the electron as a particle, it stops behaving like a wave. I know, right? Yes?
How does the laser beam affect its outcome?
That's a good question. How does the laser beam affect its outcome? Well, by it passing through the laser beam, we can see which slit it went through. So we observe its particle nature. Particles have position. You can say a particle is here, a particle is there. You can't really say that about a wave, that a wave is here or there or in one particular place. It's not. So you can say very little about the position of a wave, but you can say a great deal about the position of a particle. So the more we know about the position of the electron, the less wave-like it behaves, because we can't know about both of them. And this is very hard to get your mind around. And I'm sorry I'm springing this on you after you struggled with an exam for 2+ hours. You're like, my brain was fried, and now you're doing this to me. But we are dealing with the extremely small, the fundamentally small. And the fundamentally small things obey different rules. And we can't really relate them to everyday objects because they don't follow the same rules. But the best I can do is you know, the reputation that baby brothers have, especially if it's kind of a tag-along baby brother. Andrew's 4 years younger than Emily, the next one, and 16 years younger than the oldest. So he's like almost like a pet in our family, right? And we try to keep standards fair and everything, but the fact is, Andrew gets away with stuff that the older kids did not get away with. Part of it's because I'm old and tired, and I just really don't care that much anymore about some things, like playing, you know, going back and forth over the back of the couch. The other kids have already pretty much wrecked the couch, so I don't really enforce that rule anymore. The larger children had to follow somewhat different rules than this last one. That's the best I can do for this. Electrons are so small that they get a different set of rules. Question?
Does the pattern change based on which slit?
Does the pattern change depending on which slit? What happens is, if you have a single electron coming through here, there would be a single dot on this detector, which would probably be too small to see. So what's going on here, the reason there are two lines, is that you're shooting electrons one at a time, so at a very slow rate, but you're shooting them in exactly the same way. And so this is the accumulation of all of them coming through. And it'll be roughly half on one side, half on the other. And so you could think of this like a time-lapse photography or something, where you take a picture every 15 seconds. That's not time-lapse, it's something else. But you take a picture, and there's the one, and there's the other, and so, like, you know, dots. Yeah. Kind of like that. Yes?
Did they try this with electrons because they're so small compared to protons, or did they try it with protons? Why did they choose electrons?
I think they chose electrons because electrons were easiest to deal with. It's easy to get electrons to shoot out. We mentioned earlier, if you shine light that's intense enough and of a certain energy at a piece of metal, it will just pop electrons out. The protons are in the nucleus of the atom. And so unless you're dealing with a hydrogen ion, to get a single proton out, you're going to have to get into nuclear chemistry, and yeah, I think that's probably the biggest reason. But you could theoretically do it with a proton as well. You can't really do it with a neutron because you need the charge of the particle to be able to accelerate it. You can't take a neutron and get it to move. Yeah. The details of how they do all this is pretty interesting. But they were doing experiments like this back in the 1920s. It's pretty crazy. Any other questions? So this is called the uncertainty principle. Heisenberg's uncertainty principle. The more accurately you know the position of an electron, the less you know about its speed, and vice versa. So this is just his equation, and we're not going to do any calculations with this, but let's just look at what this means. So delta x, x is the position. Delta x is the uncertainty in the position. Delta v is the uncertainty in the velocity. So you take the uncertainty in the position times the mass times the uncertainty in the velocity, and that is always going to be larger than a constant. This is Planck's constant divided by 4 pi. Why? We don't care. It's just a number. But this is a constant. This product is a constant. So if this one gets smaller, that one has to get bigger. If the uncertainty in velocity gets smaller, then the uncertainty in the position gets larger. So you can't know both things about an electron. You can't know where it is and how fast it's going.
I'm
Yes?
sure that there is a homework problem where we have to calculate the uncertainty.
Is there? I'm sorry. I won't put this on a test. Definitely not.
Can you go over how to calculate?
How to calculate? Well, to calculate, m would be the mass of the particle, and delta v would be the uncertainty. They'd have to give that to you in some way. And delta x is the uncertainty in the position. My guess is they'd have you either calculate the uncertainty in position or the uncertainty in velocity. H is Planck's constant and divided by 4 pi. This product just has to be greater than that. I'll look at the homework. And if I forget to look at it and you have a problem with it, text me and let me know and I'll evaluate that one. Okay, classical physics, Newtonian physics, holds that particles move in a path determined by the particle's velocity, its position, and the various forces acting on it. And this is called determinacy. So the present state of this particle determines what's going to happen to it in the future. If you're throwing a baseball, it has a position, it's in your hand, you're applying a force to it. Once you let it go, it will have some momentum from that, but it also experiences the force of gravity and some wind resistance, and all of these are factors, and we can predict what's going to happen with the baseball. Because of this uncertainty about the electron, we can't predict the path that it will follow. And so this is called indeterminacy, the opposite of determinacy. The future can only be described statistically. The best we can do is describe the probability that the electron will be found in a particular region. They use statistical functions and probability distribution maps and all kinds of crazy math that I don't like. So the equations for this get kind of crazy. Here again, though, electrons behave somewhat like my son Andrew. So I'll draw you a picture. Here, let's get a whiteboard going here. Okay, so roughly speaking, this is the shape of my house. Here's the front door, somewhere in there. Okay, so let's say Andrew is at home, and I need a different color. His family color is orange, because orange implies caution, danger. So if you were at any point to just pinpoint Andrew, maybe he's there. Okay, and then you wait 5 minutes, and where's Andrew? Well, he's over there. Where's Andrew? Where's Andrew? Okay, and you may find that there's a lot more dots in certain places because the TV's over there. And he always likes and comes to sleep in my bed with me, but sometimes he goes to the bathroom. But then every once in a while, he's outside. When he was 2, he went across the street, stole the neighbor's big wheel, and drove it 3 blocks to my brother-in-law's house, his uncle's house. Is that something you would predict? Is that something you tell your child? Do not take the neighbor's big wheel and drive to Uncle Kent's house. No, it's just like completely random. And those are the sorts of things that Andrew does. You just never know. This is a little how electrons are. You can take a picture of them and say, yes, it's right there. But if you know where it is, you don't know what it's going to do next. You can look at its wave form, its velocity perhaps, but then you can't say where it is. So I hope that helps. We can also talk about baseball. So here's a picture of a pitcher throwing a baseball. The pitcher throws the baseball to the catcher. And we can describe this with classical physics. We're going to assume he's not doing a slider or a knuckleball or something fancy, but even those things can be described by physics. He's just throwing a straight fastball. So we know where the ball starts, and we can predict its trajectory based on its velocity and the effect of gravity and all that good stuff. That's how we're able to catch a ball. And little children haven't gotten the experience yet to predict where the ball is going to go. And as you get older and get hit in the face with balls more often, you learn to predict where the ball's going to go. And that's how the outfielder can catch this fly ball. He sees where it was coming, and he is able to predict where it's going to come down. Some of us are better at it than others. But your brain is doing all kinds of calculations, and you don't even recognize it. But it's computing where that ball is going to go. Predictable. Electrons are not like baseballs. If we could, which we can't, if we took an electron and threw it at that catcher, and if we threw it exactly the same way, think of a pitching machine. You get a pitching machine there, and you have it spitting balls. They come exactly the same place every time, right? It's the same. It's predictable. If you put electrons in a pitching machine, they would not always go to the same spot. Because they are indeterminate. We can't know the position and the velocity at the same time. So this is what we would see by throwing electrons exactly the same way. We would see a cluster of them here. About 40% of the time, they'd be within this circle, 20% within this circle, 70% of the time within this circle. But just like occasionally Andrew's like 2 blocks from home, it could be out here as well. It's just probability. It's not that it has to be there, but it will probably be there. Whereas if you throw a baseball in exactly the same way every time, it's going to go to the same place every time. And electrons don't do that. Any questions?
Why don't they go to the same place again?
Because they're indeterminate. We can't know their velocity and their position at the same time. And so we cannot, their current position and what's going on with them does not predict where they'll be in the future.
Why not?
Because they're too small. They don't obey the same laws of physics. It's not a satisfactory answer. You will not completely understand it during this semester. I don't completely understand it. I'm not sure if there's anyone who really completely understands the behavior of an electron.
It kind of defies logic because we know if we throw something that ends up where we
Right.
intend to throw
Yeah.
it. So.
It kind of relates into Einstein's relativity theory. When you get to extremes, behavior changes. So when you get things that are smaller and smaller and smaller, when you get down to the size of electrons, the rules have changed. And it's very hard to get your mind around. Very hard. We like Bohr's model, Bohr's model where the electrons are flying in circles, right? Nice little orbits. Like, yeah, that was good. Unfortunately, it doesn't work. So we got to go with this other stuff.